So this is going to be a quick technical overview of some new Covenant opcodes that I recently proposed. I have a BIP for them, but I know people don't like to write BIPs, so the title of this was kind of like TXHASH TLDR for those that don't want to read the BIP. So it's a proposal for 2 new Covenant opcodes, maybe 3 new Covenant opcodes. We'll see that in the end of the talk. So who am I? I was just in the next room, so I'm not going to say it all again. I was at Liquid, Roose Bitcoin, and also working on ARC. So I'm going to start with a brief history of this proposal because it's not really my idea. It was proposed originally in the mailing list by Russell O'Connor as a general idea, like, hey, we can do maybe this. And then for a long time, nothing really happened. And then I thought it was a good idea, and I kind of formalized it in a BIP and implemented it in a few places. And now I'm mostly waiting for feedback, which in the last, since it's been out for 6 months, hasn't really come too much. I know some people in here actually left comments, but there was very few. So I'm here basically asking for feedback because this is all mostly my work, and obviously a single engineer makes a lot of mistakes. So the idea is actually a variant of the Covenant proposal. Most of us know CTV, check template verify, which is kind of like a way to do pre-signed transactions, but without the signatures, right? So you basically specify an entire transaction, almost everything about the transaction, and you're gonna kind of commit to that as if it was pre-signed, but without the signature on it. Kinda, because there's a few things more you can do with that signatures currently can't. So it's kind of this idea of predetermined transactions. So the entire transaction is fixed, and you commit to that the transaction beforehand. And the nice thing about CTV is the code is really simple, right? It's basically a single hash that you commit to. You calculate it like this, and then you check if that hash actually matches the thing that's on the stack, and that's how you commit to the transaction. So that's really nice. But it's also very limiting. So TXHASH is a generalization of the CTV concept. So instead of only being able to commit to exactly this set of things, like in CTV, you can actually choose pick and match or whatever the things that you want to actually commit to in the transaction and the things that you want to leave free for the protocol to fill in later on. So in order to pick the things that you want to commit, we introduce this concept called a TX field selector. So it's, like the name says, a way to select the fields from the transaction that you're interested in. So the proposal actually introduces 2 new opcodes. One of them is going to be TypeScript only, TXHASH, and you basically give it a field selector, and then it pushes the actual hash that it calculates based on the fields you selected and puts it on the stack. The other one is check TXHASH verify, which is basically another way to do this, but is compatible with SegWit v0 and Legacy, where you take the hash and the field selector of the stack, then calculate the hash and make sure that the hash is the same as what the user inputted. So TXHASH verify looks very much like CTV, but with extra flags, and TXHASH gives you a way to play with this thing on the stack later on. Yeah, so this is how it works, right? So you pass the field selector in TXHASH and you get the hash, or you pass the hash plus the field selector into this, and it says yes or no. So okay, so how does the field selector work? So this is kind of a diagram that I made of everything about a transaction that could possibly be interesting, and then the bits that are committing to them. I'm going over them one by one, right? So we have 16 bits that we want to get everything into. So we're going to start with the version and the log time, which are global fields, obviously useful. Then there's a few fields that are related to the execution of the script, not necessarily the transaction, but they're useful because in all of the signature hashes, they're also committed to, and they are useful to control what's actually happening in your script in the context of your transaction. So it's the current input index, the control block, which holds the mass tree, so all the scripts, then the explicit spend script, which is very useful in SegWit and SegWit v0 and legacy contexts. The last script, opcode separator, no one knows why, but it's everywhere in all the SIG hashes, so we also have it. There's one bit we're not using currently, then the control bit I'll come back later, and then you have some fields of the inputs. We have the prevouts, which commit to the previous transaction. We have the sequence numbers. We have the script sigs. They're currently usually empty, but you never know. We might give them some meaning some point. Then from the previous UTXO that you are spending, you can actually commit to the script pub key and the value. We're also including the annexes because they're obviously going to have some meaning at some point, right? I mean, we have them. And then on the output side, it's a lot simpler, just script type key and value. And this is how we, like, you input these 2 bytes, you have the 16 bits, and setting the bits to 1 or 0, you can actually commit to these fields individually. And then there's multiple inputs and multiple outputs. So then, additionally to those 2 bytes, you also have a way to specify which of the inputs specifically you're interested in and which of the outputs specifically you're interested in. So first of all, you can commit to the number of inputs of outputs if you want. Like, is there 4 and I want the first 3 or something, right? So you want to know how many there are, or you don't. Then there's 3 special cases we define. So either you don't want any, but maybe you want the total number of them, or you want all, or you want the current, right? They sound a lot like the SIG-hash flags, like all, non, and single. Then you also have the option to pick like a prefix, like the first n, right? This can go up to 8,000. So you can say the first, whatever. And then you can even pick individual ones. So you can say the first, the 8th, and the 9th. And you can do this with absolute indices and relative indices. So you can say the one before me, the one after me, the one 8,000 after me. These numbers are just because the number of bits we have free, those limits. I don't know if you even can have 16,000 upwards, but. So the nice thing that this proposal has, it's actually very compatible with CTV. Because we define an empty field selector, like if it's 0 bytes long, we actually pick a field selector that is equivalent, more or less, not byte for byte, but equivalent to CTV. It commits to the same things. We call this the template default, and then we add one extra default that is the all case, which is useful if you would ever use this for signatures, and it basically commits to everything. I'm currently working with Brandon to maybe add a whole bunch of more like special cases, because we would like to have more usage of single byte field selectors instead of 3 to 4 or 5, 6 bytes field selectors. But currently in the spec we have just the template one and the all one, but we're trying to optimize it a little bit. So not only can you use this to commit beforehand on something that your transaction could look like, but if we have something like check from stack, you can actually use this hash as a super pimped version of a SIG-hash, because we have currently 3 SIG-hash modes. We have none, single, and all, and then we have the anyone can spend flag, where you can play a little bit with what you commit to. But with this, you can actually use this as a SIG-hash flag and commit to anything you want. So it's basically a SIG-hash, basically whatever goes into the SIG-hash, into the signature, similarly. So if you have check from stack, you can do a signature TXHASH. Oh, here I missed the field selector, sorry. Can you see the cursor? Here needs to be the field selector first. But you can get the hash and then check the signature over that hash from the stack. So obviously you have SIG-hash all, that's why we include all. And then you have template, which kind of behaves more or less like APO. Probably people are going to say no, but it's kind of similar to useful to APO. That's how people with L-enhance wants to do APO style things with CTV and check from stack. And this can basically do anything like other SIG-hash proposals that have been made, like SIG-hash group. With TXHASH, you can do all those things because you can pick any of the outputs and inputs that you want. So it's very important when you do SIG-hashes that you commit also to what you have committed, so that people cannot swap things around, oh, you committed to the first input, but then actually you use it as an output, right? So the control bit that we saw before, you use a control bit to specify, I also want to commit to the field selector itself. And another cool thing that we heard about today that this could enable is stacking. This morning, Rusty talked about stacking, and TXHASH actually enables stacking automatically, because you can say everyone has a certain number of inputs and outputs, and you can just say I'm committing to my input and my output, and then using a way where you provide a whole lot of different signature based on where in the configuration you are, and then some coordinator can take all the signatures, pick the right one based on how the transaction actually looks, and then you can make one big transaction where a lot of different people have actually committed to just their share of it, and then the coordinator can put a fee on the bottom and then broadcast it. So you use the individual selection mode for this. The way you would do this is that the first input commits to all your output, and then the other inputs would just commit to the previous input to also be there to make the scheme efficient. And then you provide a lot of different SIGs, and then the coordinator puts them together to like make sure that the configuration just works out. So probably like you're gonna say like I have 2 input, 3 outputs, so I'm gonna like say I want the 2 at the same height, and then the other one I just sign 1,000 times like +1, +2, +3, +4, and then the coordinator can just like pick the right one. It's a bit of an inefficient way to do stacking, but since this is all off chain, doesn't really matter too much. It's like you want to sign just your part in the transaction, and then someone can take all these parts, make a single transaction, and then stick the fee at the bottom, like stack all the bundles together, and then stick a fee at the bottom and broadcast it, right? So you only, like you want to have a transaction with 2 inputs, 3 outputs. Instead of making a transaction, you just make like a bundle and you sign only for your stuff. You send it to me, and then other people also send this to me. I bundle this all together because you're only committing to your stuff, and then I commit to everything, and I add the fee, right? And the nice thing about this is that it's not miners doing this. Anyone can do this, any random operator. And the actual fee still gets paid. Well, the actual fee still gets paid over the normal mempool, and you don't have to be a miner to do this. Like any wallet can do this. Any question? That's a good question. That's a good question. Exactly. Yeah, so even if you're not stacking, one of the main benefits, I don't have this in my slide, one of the main benefits of TXHASH over, for example, CTV is that you can just say, I have 2 inputs, 3 outputs, I commit to all that, but I leave space for even myself to just add fees, right? So with CTV, you need to commit to everything up front. So you don't know how much fee you're going to have to pay because you don't know the fee rate. So what usually you would do in any construction using CTV is you leave an anchor output that then you're going to spend later on. So you're going to first broadcast this with the anchor output, spend the anchor output, and then pay the fees from the child using child pays for parent. But with TXHASH, you can just make the signatures only commit to the things that's important, and then you can put your own input, adding your own input and your own output, and pay the fee later on. So that's a way how you could do it for yourself, but then actually with stacking, you can get all of those bundled together.
The way that I've always thought about it, maybe this it's basically redoing the SIG hash system, right? Like the SIG hashes tell you which bits you're signing on.
Yeah, exactly.
Because there have also been the like crowdfunding type transactions you're doing kind of something similar to something. So it's always been that.
Yeah, exactly. So the SIG hashes are very useful for anything like order matching and this like distributed order book kind of things where like I have my stuff that I care about, and like I just want to make sure that I receive something from someone in return for something that I sent, right? You can do all of these things using this as a SIG hash. So the main concern that comes up when talking about this is quadratic hashing, right? So what if a transaction is really big and you can just put this field selector on the stack, call TXHASH, and you're going to have to hash like thousands of bytes because like you're actually referring to some things in different previous transactions. So all these outputs can be really big, your script sticks can be really big, everything can be really big. And if you're always going to hash this, you could actually get like what they say quadratic hashing, because then for every input you need to hash all those things, so it's like n squared, and then you need to hash a lot of things. So one of the main like technical challenges in this proposal is how to avoid this quadratic hashing exploit. But we have a way now, it's implemented and described in the BIP using the reference implementation, where you don't have this problem. What we're doing is we have a lot of caching at different levels. So first of all, we're going to cache all the variable-sized fields. That's kind of similar to what the SIG hash does, but then individual. So all the fields that can be of any size, we're going to hash them at most once, which means that if someone tried to exploit and like get the same fields multiple times in a row, all the variable-sized fields will always be just 32 bytes because they're already hashed. And it means that for every transaction, you're going to hash those at most once. And that's kind of amortized, like that's how the SIG hashes also do it. Every time, any transaction, you just pre-calculate all those hashes. For the SIG hash, this can be done lazy. So every of those items you only hash once. And then after you have hashed all the big items once, then the amount of data you're going to hash for each invocation has really clear bounds, because the amount of inputs you can select is bounded. And then also for the leading, I don't know if I have this here, for the leading thing where you like say the first n, we're going to also keep a cache where every interval, like every 10, for example, you keep the intermediate cache, so that if someone asks for the first 90 and then asks for the first 92 and then for the first 93, you keep the hash of the 90, and you know you're gonna always only at most have to add 9 of them, right? Because you keep a cache for the 90, for the 100. So if someone asks 96, you're gonna have to hash 6 more of those values, but it's always bounded by 10. So we're going to also incur a cost for this opcode, just like checksig costs you 50 validation budget. I recently bumped it from 15 to 25. I might change my mind again and bump it back to 15. But if we get this great script restoration, we're going to probably use the Varos budget for this, which makes more sense than just picking a random number like we're doing it right now. But there obviously needs to be some cost associated with this. I thought it was fair to have half of the checksig, because like with a checksig you kind of do this as well, and then you do EC. And it turns out they're kind of almost equal for like slightly larger amounts of bytes. So like, yeah, you get a budget, and if you do this like a lot of times, you're just gonna run out of budget. So what's the status of this? I recently got a BIP number, thank you. The BIP has been written. It has a reference implementation and some test vectors. I say maybe test vectors because it's quite rudimentary. There need to be a lot more edge case test vectors. So this needs a lot of review. There's an implementation in Bitcoin Core and Inquisition that also needs a lot of review. There's also an implementation of the caching in Rust Bitcoin. Kind of also needs review, but it's like not as important. Please review the other things. And then one last thing I want to talk about. So like we defined this field selector, right? We defined a logical way to point at things in a transaction, and that's kind of useful. And another way we can use this for maybe is with another opcode, maybe OpTX, which I think originally was proposed by Rusty in some mailing list posts, which basically means you take, do I have it? So you take the field selector from the stack, and then instead of hashing all the things that the user pointed at together, you basically put them on the stack, right? And then the control bit that we were using for the hash to include the field selector, we can actually repurpose this bit to let the user choose between wanting to put all the fields on the stack together or all the fields individually. And this way we get direct introspection opcode, where, for example, if you want to look at the sum of all your output values, for example, you could use the field selector to point at all the output values, get them all on the stack, add them together, and then know the total output value, something like that. So this is useful if you want to do math on amounts, or if you want to look inside the scripts that people are using in the outputs or on the inputs. So that's something that is not in the BIP, but is something that we could be doing. And then one last thing I want to mention is if the TX field selector actually gets some use, and we notice that it's useful because it's like a generalization of anything, APO, any script, non-signal, single, whatever. So like everything can be done with the field selector and many things more. So maybe with SIGHASH group, people come up with nice new things. So in SegWit, in Taproot, it's actually possible to introduce this as a new key type where you can add the field selector as a SIGHASH flag. Instead of adding 1 byte, you can add any number of bytes depending on what you want to select. And then the signature just checks using the SIGHASH. So you don't have to use the opcodes, but you can just directly use it as a SIGHASH. And that's my last slide. So yeah, please review. I go back here. Need review. Thank you. Questions? Yeah.
So where does this sit with like all the other proposals? Like how does it play well with that sort of like, best case?
Well, it's definitely less popular because otherwise I would have been sitting here this morning. No, I think it's somewhere in the middle. I mean, direct introspection is definitely more useful than this, and CTV is definitely less useful than this. So like, it's kind of like a better version of CTV. It gives you like a lot more things. It's also a lot more code. I think it's sitting in the middle. You can do most of the things with this. The only thing you cannot do without OpTX is math on your inputs and outputs, right?
But I'm guessing the main reason you propose OpTX is just because we don't have a cat. Like what's the reason?
Exactly. I don't know, but I think even if you have only OpTX, you also want TXHASH because you want to sign over things very easily. Otherwise, if you have to do the hash, like actually exactly like Rusty said in his talk, if you have to do the hashing on the stack with OpTX, you're going to like do all the hashing multiple times, and then if you're actually getting a fair budget, you're going to run over this budget very, very easily. So it's very useful that you have a cached version of all this information, and then you can very easily just query it and get the hash. Ha 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 ha.
I guess you're computing ahead of time that field selector hash value, or
Yeah.
witness, or
Yeah, yeah.
in the script, if you know what I mean?
Yeah, so the programming paradigm with cat is you have the sig hash we have right now. TXHASH is kind of like a sig hash. So the sig hash points to a certain number of fields. And then you basically find a way where you can prove that the thing that's on the stack is actually the sig hash, right? And then you're going to inspect the different parts of this and then assert them. Assert that this is actually equal to this. So what you do with TXHASH is like the things you want to be equal to something, you actually put them into this like hash engine. It calculates the hash. You say like, I want the first output to be this script, second output to be this value, whatever. It gives you the hash and the field selector that you actually picked, right? So you pick the fields in the field selector. The whatever engine will give you the hash. You put that in your script, and then the user who wants to spend this actually needs to fulfill these values, and then you check the hash and then you do that.
Basically, like in the script, it's fully validated. You already compute the field selector and the hash. It's up to basically the user to make a valid spend that satisfies that, right? So it's like
Yeah.
So like there's no open argument. Like for example, like a check ticket open argument is look. This one there's no open argument because.
But the open argument is anything not committed to, right?
Okay.
Like you commit to certain things, and everything else can just be, yeah. But that's only in the check TXHASH verify case. You can also use it as a sig hash where you basically says TXHASH check sig from stack, and then the user can say, here's my signature, and this is the things that I committed to. So like this signature is valid for any transaction that actually fulfills the things that I want, just like with a sig hash, and then you can do it that way.
So when people talk about this, it seems strictly better than almost every other proposal. Seems to be, I don't know.
Yeah, but it came from me and Russell O'Connor. No, I don't know. Yeah, I should do an NFT. No, I don't know. Yeah.
Using this, or like sort of like something more complex than like base programming, just to get a feel for sort of like the ergonomics of that kind of. Because my understanding is like you have one that's basically no covenants, and you have one that's also based on the liquid opcodes, which is basically the push instead. Did you look at potentially doing, or is it sort of like time, cost, R&D kind of a thing that's there? Because I think that would help to move it forward, basically, perhaps.
Yeah, I think
you
it wouldn't be too hard.
Sapio, which Jeremy worked on, perhaps, and like plug this instead of that. But that's an idea.
Well, yeah, that's not something I want to spend time on. But I could. No. The thing with Arc is the current design of Arc, the TX IDs of the leaves need to be fixed. Right, so that's something TXHASH doesn't have. Like TXHASH lets you commit to certain things you want, but the fact that all the other things can be anything else, it means your TX ID is like in no way not possible to know. So for the naive covenant version of Arc, we would really want the TX IDs to stay the same. So we actually are better off with CTV. But the default mode for TXHASH is also CTV. So like we could definitely use this instead of CTV. I mean, this is CTV plus whatever. So yeah, I don't think it would be hard to change the implementation and just have a proof of concept version with CTV.
Just a first comment, a not tongue-in-cheek answer to the question, and then a question of my own. I think the answer about like why not this over the others is like. I wanted to see the BIP, and I mean, it was just put up in October, right? Look at the number, it's 346. CTV is BIP 119. I know the numbers don't indicate everything, but I mean, there is a big time scale.
It's older than Cat.
Yeah. Right, exactly. Like, yeah, Cat, I mean, one of the reasons that's getting a lot of excitement now, partly a big marketing budget, but also Cat was in the original Bitcoin. Like, we know exactly what it looks like. It's been well researched. ATX and TXHASH was proposed in a mailing list as like a theory that could do a lot of these things. And I would say like one downside, it's not really a downside, but it makes it like require more thought, is it's more complex. I think like one of the original advantages of CTV, I know that when Jeremy was first working on it, was like there's a subset of things that we know we really want to do, and then there's more that we probably want to do, but as you add that complexity, it's harder to evaluate. So let's focus on this really simple thing. I know it's not enough, right? So I think these are all like important things to evaluate when we're thinking about the proposals. This is like strictly more complex, which is part of the argument for it, but it's also like, well, let's wait and see. And one of my questions is kind of related. There's some question too, like it takes slightly more space to do the CTV stuff with TXHASH because it's a little bit more open, right?
No. That's one specific purpose of the protocol is to make it like exactly backwards compatible. So if the field selector is empty, we just pick one that's equal to CTV.
No, I mean,
we might come back on that.
Oh, if it's empty, so then it would be this. It would. If it's empty, then it just does CTV.
Yeah.
Right.
You still lose the 1 byte for the empty stack element, maybe.
That's what I thought. It was basically like I remember seeing something, and again,
no,
like it's
true.
still
that's
going
not true
through
because
iterating.
CTV takes 32 bytes and we also take 32 bytes. But 32 plus 1, right? Yeah. So it's exactly the same as CTV.
Bitcoiners tend to care a lot about 1 or 2 bytes.
No, it's exactly.
Maybe to our detriment. Though. I'm not
Like,
saying that's an argument against.
The byte cost is exactly the same as CTV.
Okay.
But we might come back on that because we might want to like have something else for the default one or something like that. But let's see.
Right. I remember that coming up at one point. But again, this has like been.
But like to come back to the
active
things you
development.
said earlier, I think this might even be one of the most recently formalized BIP proposals. Like APO is very old, CTV is very old. Volt was slightly before this. TLUV, well, never had a BIP, but like was talked about. Yeah. Well, no, this was talked about way earlier, but not formalized. And yeah, you're definitely right. Like cat is like how many lines of codes? One handful. This is this plus another bit of like this, but like CTV is very little code. The code for TXHASH, conceptually, you need to think about it because like you need to make sure the hashing all like checks out. The code is quite verbose, right? It's just literally caching for every field, so it's like copy, 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 copy. So like yes, it's a lot of code. It's like 500 lines of code in a file, but it's just like a cache for this field, a cache for that field. So it's like kind of stupid verbose code. But yeah, I think the complexity is definitely a reason why people don't want to look at it. I think also a reason why people don't want to review BIPs or code related to covenants is because covenants are controversial, you know, I mean. Like, yeah, I think when I put out the BIP and the implementation, I got more feedback in private messages than on GitHub because people just don't want to be reviewing or be associated with any of these proposals because if you review it, maybe you're going to be associated thinking people are going to think you condone this, whatever. I mean, it's all politics, right? And it sucks. But
I mean, the hashing or the caching is an interesting complexity of it that I don't think a lot of people think about. And I think there was that one pseudo bug that was identified in Jeremy's BIP 119 that had something to do around the caching. It was like an edge case that could never be run into, but I think AJ identifying because he was writing out some test fixtures. Mm-hmm. But it's like in a lot of these things, that's the most complex part. And because there's more kind of like you know exactly what you're going to cache with CTV. Yeah. That's also a bit that's simpler.
Yeah, I think with CTV at some point he had singles, so then you can never cache the hashes because you need to leave out. I think the current one he zeroed it out or something, so you always had to hash a certain number of things.
Yeah.
Again. Yeah.
Okay. Thank you. Sorry.
More questions? Otherwise, thank you very much. There's one more question.
Why 25?
25 what? Why 20? I don't know. Like, I think I spoke with Peter Will, and he said a C operation is roughly equivalent to 10,000 bytes of hashing, and 10,000 bytes seems like a reasonable upper bound. I first thought we were never going to hash 10,000 bytes every time, so I put it at 15. But then it's like, well, you can actually make it go a little bit over. Well, maybe not because the bounds are pretty clear, but why not? I mean, I definitely think we should move more towards the VAROPS model where it's like an actual reasonable cost and not just like just random like,
number,
yeah, just throw a number. Yeah. I mean, it can be 10, 15, 20, 25, I don't know. It needs to be something that's non-zero so that people just don't throw like,
It should be between 0 and 50, basically, is what we're saying, right?
Well, yeah.
Because 50 is the SIG-off for, normal signatures, right?
Yeah, between 0 and 50, but it's not 0 and it's not the same, right? So, yeah.
That's interesting.
Cool. Last question. Thank you.